The problem I want to solve for you today in this and the following videos is a problem which has very interesting industrial applications. The point is that we have steam at high pressure and high temperature. We could either send it through a nozzle and gain velocity from it, or send it through a turbine and gain work from it, or alternatively, we could send it through a throttling valve and just lose its pressure without gaining any work or any velocity from it. We would try all these three cases and see how they compare. Well, the problem starts with steam at high pressure and temperature. So we have steam at high pressure and temperature. Pi equals 2 megapascal and Ti equals 350 degrees C. Now we send it through a nozzle first. So it is a nozzle, and AI, the initial area or the entrance area for the nozzle, is 7.5 square centimeters. So this is our nozzle, and our nozzle is expected to change velocity. A nozzle is the instrument that increases velocity and reduces pressure. So VI for this nozzle, VI equals 55 meters per second, and VE equals 390 meters per second. And what we need to achieve such change in velocity is the pressure difference, and therefore at exit PE equals 0.8 megapascal. And now what we want to do is to solve all thermodynamic equations for this nozzle and see how much irreversibility we get from it, and calculate different nozzle parameters. Later on, we would send the same steam into a turbine, and instead of gaining some velocity difference, we would gain some work. And finally, we send it to a throttling valve and see what happens to it when it goes through a throttling valve. Well, if the pressure is 2 megapascal and the temperature is 350 degrees C, I would dare to go directly to the superheat table for a steam. Why? Because I remember that P critical for steam was about 22 megapascal, and T critical was about 373 degrees C. And so the temperature is very similar, almost close, but the pressure is far less, and therefore we expect it to be superheat. Now, another look at the table. In superheat table, we see that for the pressure of 2 megapascal, the saturation temperature is 212 degrees C. So 350 degrees C is far higher than the saturation temperature, and therefore a superheat condition is correct. Now, looking into the superheat table, we would see that for a pressure of 2 megapascal, for a pressure of 2 megapascal, actually the temperature of 350 degrees C is exactly right in the middle. So what we can do is to just move to this line. This line where my pointer is showing, and just read these values for the uh, conditions that we have. So for P equals 2 megapascal and T equals 350 degrees C, the data that we get from the table is that specific volume VI equals 0.13860 cubic meters per kilogram. HI equals 3137.7 kilojoule per kilogram, and SI, these are all entry conditions for steam into our nozzle, and SI is 6.9583 kilojoule per kilogram Kelvin. So these are properties for 2 megapascal. It's a good job to uh, know what saturation properties for zero point 0.8 are, since we have only the pressure and we don't know if the final condition would be saturated or superheat. So it's good to know the saturation condition right here. Well, 800 kilopascal or zero point 0.8 megapascal is just on the first line. So for P equals 0.8 megapascal, the saturation temperature Tsat equals 170.41 degrees C. Vf equals 0.00115 cubic meters per kilogram. Vg is 0.24035 cubic meters per kilogram. Hf equals 720.87 kilojoule per kilogram. Hg equals 2768.3 kilojoule per kilogram, and Sf is 2.0457457 kilojoules per kilogram Kelvin, and Sg equals 6.6616 kilojoules per kilogram Kelvin. So these are all the properties that might be of interest to us. Well, let's see what you have got on the TS diagram here. As you know, the saturation line is fairly symmetric on the TS diagram. Now, you see the critical point is 373 degrees C. Our point is 350. So if I put point I, since we have put I as the entry point, and this pressure line is 2 megapascal. Here P equals 2 megapascal, and this pressure line P equals 0.8 megapascal. Well, our next step is to simplify the governing equations. And for this problem, we need the first three equations, the first three. As for a nozzle, the first step that we have to take is to decide on a control volume. And the point with the control volume is that usually for nozzles, they draw the shape of a nozzle as a converging channel. They call this a nozzle. Although we shall later see in the compressible flow part that nozzles could be converging or diverging. But just schematically, nothing true. And with knowledge of that point, still usually a converging nozzle is a symbol for a nozzle, a converging channel is the symbol for a nozzle. And so this would be a point I, which is the entry point, and this is point E, which is the exit point, and our control volume would be here. The nozzle has steady flow, so flow enters this nozzle steadily and leaves it, so there is no steam that remains inside this control volume. All that enters change properties, but leaves from the other side. And for the equation as you see it here, the all left-hand sides would be 0. This left-hand side would be 0, 0, and 0, since the nozzle is steady. Usually, at least in the thermodynamics lectures, we study steady flow, or we integrate between some initial and final condition. For the present problem, we study steady flow, so therefore all left-hand sides would be 0. The change in elevation is negligible for a nozzle. The change of elevation is negligible for a nozzle. And in nozzles, we have no heat transfer. Basically, what we want to do is to use the energy, the steam energy entering the nozzle for increasing velocity, and we don't want to lose it by heat. There is no work since there is no moving parts. There is no work for it. There could be some entropy generation, and we shall look at it pretty shortly in simplifying these equations. So, for simplifying the equations, the first equation is the mass conservation, and its simplification would look like that: 0 equals m dot I minus m dot E. So the mass that enters the control volume would also leave it. Entry and exit masses are the same. We could conclude that m dot I equals m dot E. And instead of writing in this way, there is another way that we could write it: equals, instead of m dot I, we could write AI VI, which is the velocity, divided by VI. This is velocity, this is a specific volume, and that equals AE VE divided by VE, velocity and specific volume. Well, the first law of thermodynamics, again, is 0 equals m dot, which is of course the same between entry and exit, times hi plus vi squared over 2, and the change of elevations negligible if there is any, because in many cases nozzles are horizontal and there is no change in elevation, and we are not ignoring anything. And the same is for the present nozzle. Minus m dot times he plus ve squared over 2. And there is no heat transfer or work, so the other two terms vanish, and therefore we conclude that he would equal hi plus vi squared over 2 and minus ve squared over 2. That is exit enthalpy. As you see, we have all terms in this equation, and therefore it's possible to calculate it. We shall do it later on, but the third step that I shall take, the third equation that I shall simplify, is the second law of thermodynamics, and that tells us that 0 equals m dot I Si minus m dot E Se and plus S dot J. And this is the second law of thermodynamics. Now, for all these equations, we have some values that we can um, place in them and see what the results are. You see, for entry flow, we have A, B, and B, so we can have m dot. Here, all three terms on the right-hand side are known, and therefore we can calculate H. And here, these two terms are known, and therefore S dot gen would equal m dot times Se minus Si. And all terms are known. The left-hand side is possible to calculate, which I shall do it in the next video. Thanks for watching, and see you in the next video.